Let us write one more expansion and then we can take some important final conclusions. The next expansion will be a simple trigonometric identity of 2 sin A sin B and 2 cos A cos B. So let's first apply 2 sin A sin B. So I'll keep the first term as it is, minus sign as it is. I'll keep J1 mu F outside, and we have this 2 is already there. So 2 sin A sin B. The formula goes something like this. It becomes cos A minus B, which is omega C minus omega M T first, minus cos A plus B. So A plus B will be omega C plus omega M T. Next will be J2F written as it is, J2 of mu F. And I'll take 2 cos A cos B. The formula goes cos A minus B. In this case, it will be omega C minus, you can see the second term is 2 omega M. This time it is plus cos A plus B, which is omega C plus 2 cos omega M. So 2 sin A sin B is cos A minus B minus cos A plus B, and 2 cos A cos B is cos A minus B plus cos A plus B. And likewise, I can keep writing the terms. I'll write one more term, J3 mu F into, now we have 2 sin A sin B again, so it's cos omega C minus 3 omega M minus cos omega C plus 3 omega M. And this will simply continue. And now you can see every term in the expansion is individual independent sinusoidal term. So we can now simply understand what are the frequency components present in the FM signal. So let us plot the various frequency components that we have in the FM signal. We will plot the magnitude of the frequency components versus frequency F. Right now we are not very much interested in the magnitude axis. We will just put the various frequency components on the frequency axis, and that too only on one side. So we are drawing one-sided representation of the frequency spectrum. You can see that the very first frequency which is present is cos omega CT term, which gives you the frequency of FC. Let's say FC is present somewhere here. So this is the original carrier frequency present FC. So I'm now collecting frequencies in the form of F measured in hertz. So we have written terms in the form of omega. If you divide omega by 2 pi, you get frequency in F, or you can simply write omega as 2 pi F. In that case, the terms will be converted in the representation using F. So you can see omega C minus omega M and omega C plus omega M will correspond to two frequencies on the two sides of FC, and these two frequencies will be nothing but FC plus FM and FC minus FM. And you can see it doesn't stop here. You have so many more frequency components. So after taking FC minus FM and FC plus FM, the next set of frequency components is FC minus 2FM and FC plus 2FM. So if we plot them, they will be on the other two sides again. So the next frequency is FC plus 2FM and FC minus 2FM. And I'll just plot one more set of frequencies, which is in the form of FC minus 3FM and FC plus 3FM. So that will appear next to it. So this is FC plus 3FM and this is FC minus 3FM. Now we have not shown the amplitude of the frequency lines as per the scale. So you can see that we are not going to draw any conclusions on the amplitudes from the figure. We are only interested in the frequency components as of now. We will have discussion on the amplitude of each and every frequency component in the later clip. So you can see that it will not stop here. I will have many frequency components on both the sides. The next set of frequencies will be FC plus 4FM and FC minus 4FM and so on. Let me quickly remind you that this frequency spectrum was derived considering single frequency sinusoidal signal as the modulating signal. So you can see everywhere we have shown discrete frequency lines, FC, then FC plus FM, FC minus FM and so on.